Okay, it's good to be back. Picking up where we left off, scientific method. I want to go over the individual components of scientific method and bring them together to look at the big picture. Definitions and concepts will be explained in detail, and the link between each step will be revealed. Scientific method really is the heartbeat of science. It may be useful to know what's behind it. As a graduate student, one of the neatest things that I was involved in was scientific research. What was so neat about the process was scientific method. I really couldn't find anything that described how neat the process really was. So I made this up just kind of as a demonstration to show you what the process is like. There are many different versions that outline the process. The scientific method is fundamentally valuable. The process really doesn't have a rigid order, but a general path to follow. I chose these 6 steps because I felt like it really described what the process was. Number 1, observe and ask questions. Number 2, research. 3 is to formulate a hypothesis. Number 4 would be to test the hypothesis. Number 5 is to conclude the analysis. And 6 would be to share the experiment. Observations are done with all 5 senses and/or instrumentation to gather facts and empirical evidence. What is a fact? Facts are simple basic observations that can be shown to be true. Facts do not explain relationships. An example would be the sun is out. This is a fact. It does not describe a relationship, and it states something that can be proven simply. Another example would be the sun is out because it undergoes a series of nuclear reactions to cause light to shine on planet Earth. This may be true, but facts do not describe relationships. What is empirical evidence? Empirical evidence is a series of facts collected by the 5 senses, sometimes throughout the entire scientific process. This series of facts are used to account events and be referred to when research is being done. Patterns can reveal themselves with empirical evidence. Example 1 could be when someone opens some lip gloss and notices the smell of grapes. A week later, the smell appears to be less potent. An example using instrumentation could be if someone chemically analyzed the lip gloss, and a week later there was a slight decrease in a specific signal. The facts that were collected with empirical evidence include the following. Set 1, Fact 1. The lip gloss smelled like grapes when it was opened. Fact 2. The smell appeared to be less potent a week later. Set 2, Fact 1. The NMR spectra of lip gloss had a distinct signal. Fact 2. A week later, the NMR spectra had a slight decrease in a specific signal. With the collected facts, the empirical data shows that the smell may have faded. So the question would be, does the smell fade? Why does the smell fade? Why does the NMR signal decrease? What would cause the smell to fade? With the clear question, does the smell fade? A good place to start is knowing what chemical makes the lip gloss smell like grapes. This can be done by looking at the list of ingredients on a lip gloss container. From the ingredients list, a compound was found that may cause a lip gloss to smell like grapes. This can be called compound X. The next step is to search credible sources, such as peer-reviewed articles in journals, scientific databases, for research that has been done on similar compounds. From the search, it was found that compounds similar to the active compound that gave the lip gloss a grape smell evaporate over time at room temperature. So now we have 2 pieces of information. Number 1, the smell appears to fade. Number 2, compounds similar to compound X evaporate. A hypothesis is a critical point in the scientific process. It is where a statement is made that describes a relationship. This step should be done with importance on clarity. Clarity can be helpful when an argument is made on whether or not the hypothesis is rejected. The question is clear. The empirical evidence shows that the smell appears to fade. From the research gathered, we suspect that compound X may evaporate. We can link these 2 pieces of information together by using a conjunction statement, by saying the smell appears to fade and compound X may evaporate. This begins to develop a relationship between the 2 pieces of information. A good hypothesis should be falsifiable, meaning it has the capability to be proven wrong. A hypothesis should predict something. If-then or cause and effect statements can logically connect ideas into conditional relationships. and pull them out of the observation and research stage into a clear hypothesis. The empirical evidence showed that the smell became less potent over time. This could be called the consequent, meaning something that follows, or the effect. The research gathered showed that compound X may evaporate over time. We could say this is the antecedent, meaning something that exists before something else, or the causality. Connecting the dots using if-then statements, we could state a conditional relationship. If the compound evaporates, then the smell fades. This is a true statement so long as the consequent is true, and it can be proven that compound X evaporates. Sometimes it is obvious how to clearly state a relationship, but there are some cases where relationships are ambiguous, making it difficult to reveal or express in words. When the clarity of a relationship is not so apparent, two things should be considered to construct a clear statement that describes a relationship. One is premise and the other is conclusion. A premise is a proposed offer of reason to accept another claim. Words that indicate a premise is being used is since, if, or because. A conclusion is a main point that is being asked to accept. Words that indicate a conclusion is being made are therefore, thus, as such, as a result, and then. So clarify, is this a proposal that is being offered as a reason to believe another claim, or is this the main point that is being asked to accept? Using the statement, if the compound evaporates, then the smell fades, we can see how the statement fits into each category. The premise is, if the compound evaporates, because it is proposing a reason to believe another claim. The conclusion is, the smell fades, because it is a main point that is being asked to accept. Formats that can help construct a valid argument are modus ponens and modus tollens. The rules for modus ponens are that two premises are made followed by a conclusion. If both premises are shown to be true, the conclusion must be true. The first premise states that if the antecedent is true, the consequent is true. The second premise states that the antecedent is in fact true. If both premises are true, the conclusion must be true. So we have two premises and a conclusion. The logic is made simple and congruent. With modus ponens, we would say, if the compound evaporates, then the smell fades. The compound evaporates, therefore the smell fades. Now the hypothesis becomes compound X evaporates. If we can prove this experimentally, that compound X does in fact evaporate, the conclusion must be true that the smell fades. Our experimental task now is to show that compound X does in fact evaporate. This will answer the initial question, does the smell fade? This will also give a valid argument with a conditional relation that a conditional relationship has been found. This will give proof that the smell did fade. This really is an intuitive statement. It's just set up in a format that's not used in everyday life. So we can see with the diagram up here that the premise A is that the compound evaporates and the conclusion B is the smell fades. So if we want to plug in the premise and conclusion into A and B, it reveals that any premise and any conclusion can be set up in this format. At the modus tollen, you can see that it's a similar format with a premise and a conclusion. However, if the conclusion is proven not to be true, then the premise cannot be true. So this we would say the same thing. If the compound evaporates, then the smell fades. The smell does not fade, therefore the compound did not evaporate. In the hypothesis stage, we took two pieces of information, one from the research that was done and one from the empirical evidence, and brought them together. The second part, we constructed a conditional relationship, and finally we constructed a logical proof that was set up in a modus ponens format. In the experiment, a point is made to make a clear distinction of the relationship between the cause and the effect of what is being measured. How do we do this? To do this, all things outside of what is being measured are purposely set up where they do not interact, change, or affect the experimental outcome. Terms used for things that can interact with the experimental outcome are called parameters and variables. Some parameters and variables could be temperature, pressure, or the amount of substance. To give you an example, some reactions are affected by the presence of oxygen, so they are done in the absence of oxygen. These are conditional parameters outside of what is being measured that could change the outcome. As you can see here, the experiment is in the blue dot and the oxygen would be the yellow dot. What we would do is isolate the experiment so the oxygen couldn't interact with the reaction or what is being observed or measured. Parameters are set up so they will not change and interact with the experimental outcome. How can a parameter change affect an experiment? The point of an experiment is to show how A changes to B. When parameters change, they can affect A so it is no longer A. As a result, there is no longer a relationship between A and B. There is the value A that has been influenced by something else that changes to value B. Parameters need to be locked into place so they do not affect A to give a clear relationship between A and B. When a parameter is locked into place, the term held constant is used. So as you can see here, we have A and B, and the whole point of a relationship, this is just looking at it at a different view. What we want is an experiment that clearly shows the change from A going to B. When parameters change, like temperature or pressure, if it was a compound, if A was a compound, it could actually change the compound, so it would no longer be a relationship between A and B. It would be compound A that's been influenced by something, and then that influenced A would then change to B, so you wouldn't get a clear relationship. An example of reactions with parameters that are held constant would be the following. An experimental sequence was carried out where the reaction times were 1 minute, 5 minutes, and 10 minutes. The pressure, temperature, and volume were held constant, meaning they did not change. Another example of how parameter change can affect an experiment would be if we wanted to know what reaction was fastest, compound A and X, compound B and X, or compound C and X. And the reaction with X was sensitive to temperature. If compound A, B, and C react with X at different temperatures, it would be hard to determine a reaction speed because temperature can greatly affect reaction speed. However, if all three experiments were done at temperatures that were held constant, then the experiment would be more meaningful and show information about how fast A, B, and C react with X. Another good practice is making slight changes. Slight changes should be made between experiments. This can decrease the amount of questions there are between the cause and effect with each experiment. To conduct a meaningful experiment, the experiment should have what is being measured isolated from influences outside of what is being measured. Parameters should be held constant when they are not involved in what is being measured, and only slight adjustments should be made between each experiment. How can we set up an experiment with a hypothesis that the smell fades because compound X evaporates? We suspected that the good-smelling chemicals evaporated. How can a quantitative measurement be recorded when the compound evaporates? When something evaporates, liquid volume decreases and the weight decreases. So we isolate compound X and put 1 milliliter in a 10 milliliter graduated cylinder to see if the volume decreases. If we want an additional way to measure the evaporation, we can put the graduated cylinder on a scale and record the initial and final weight. This gives 2 ways to measure one experimental parameter. How long should we do the experiment? The lip gloss was noticeably less potent after 1 week, so compound X could simulate this by being left out to evaporate for 1 week. When data is analyzed from the experimental results, It will either support the hypothesis, and the hypothesis will not be rejected, or it will not support the hypothesis, and the hypothesis will be rejected. A conclusion is made based on whether or not the experimental data supports the hypothesis. Compound X evaporated and the smell faded. The experiment supported the hypothesis, so the hypothesis was not rejected. It was concluded that the reason offered for the conditional relationship between compound X evaporating and the smell fading was accepted. The smell faded and compound X evaporated. The final step is to share your study to the world for brutal scrutiny by others. Brace yourself for impact. As a scientist, the work done will be scrutinized. Sometimes this is delivered in a warm spirit, and sometimes it is not. I would not waste my time on taking it personal. What is important is using the information that is given to make improvements. Okay, looking at the steps we went over, we started with observations and questions. Once we had a clear question, we did some research to get information about the question. From the research information and observations, we came up with a hypothesis and developed an if-then statement. The modus ponens and modus tollens helped us clarify a valid argument. An experiment was constructed to test the hypothesis. The data was analyzed, and it was concluded that the experimental results supported the hypothesis. The experiment was then shared. So this is basically summarizes scientific research. We start at the observation and questions, then we go to the research, then we go to the hypothesis, then we go to the experiment, then we analyze the data, and then we share the results, and based on whether or not the data supports the hypothesis or not, we'll move forward. If it's not rejected, to have it reviewed by peers or other people. If it's not rejected, then it will keep being used until basically it's further rejected. This isn't a rigid order. We can, start and stop anywhere we want, depending on what the need is. This process chips away at any possible doubt or error. If you think of the line on the 0 mark on the y-axis, right here, as being 100% true, and the x-axis is the body of evidence that has not been rejected, the increasing body of evidence gets infinitesimally closer and closer to the truth as the body of evidence increases. So as we go this way with the increasing body of evidence, we get closer to the 0 mark where it would be true. At some point, the scientific community determines that a law or a theory can be developed. Laws and theories are similar, but they are not the same. One does not get promoted into the other, much like a rook cannot develop into a knight. A rook is a rook, and a knight is a knight. Scientific laws describe what happens. Scientific law does not explain why something happened. An example would be if two bodies move away from each other, the force of gravity decreases. This describes what will happen, not why it happened. Scientific theory describes how or why something happens. For example, the theory of relativity explains why light bends around massive objects. Okay, so theories and laws are not the same, and they do not get promoted into each other. What are the similarities? Laws and theories are very respected in the scientific community. They both have repeatability. The relationships are tested over and over with the same results. Revisability, laws and theories can be modified or tweaked as new information comes in. Predictability, laws and theories have predictive power. Fundamental truths of nature, laws and theories are held as fundamental truths of nature until further studies prove them wrong. Starting points for research. Laws and theories are often starting points for research. They can be thought of as fundamental points of science, like pillars holding up an enormous building. So each time a study is done to the scientific method, a body of evidence is developed. With the increasing body of evidence, the truth of a given phenomenon reveals itself more clearly.